Blender 3.6 has been released, and it's including a flashy new feature that will probably get some heads turning. Simulation nodes. Yes, simulation has come to geometry nodes, and in this video I will give you an overview of what to expect from the new system and how you can get started using it. There is one thing I want to make clear from the beginning though. With Blender 3.6, nothing changes in terms of how physics simulations are done for now. Rather than taking all of Blender's existing physics simulation systems and plugging them into nodes, the new feature does something much simpler, but also much more powerful. The approach is to build on the vast capabilities that geometry nodes already have and add basic functionality to turn all of that into custom simulation systems. That way, we make sure to build a solid foundation that power users can benefit from immensely already, and add more high-level features on top of that any artist can use easily later on in a way that supports and strengthens the entire ecosystem of geometry nodes in Blender. So yes, right now I should give the disclaimer that you do need some solid experience using geometry nodes to benefit from the new feature. Easier to use one-click solutions using the new system will follow in future releases. But hopefully I can give you an idea how this approach scales up to virtually infinite potential. That said, the added feature set is, for now, intentionally kept relatively compact and simple to scale it up alongside other necessary improvements in Blender in future versions. And there are some obvious current limitations, like losing the material assignment, that aren't supported yet. This is just the first major milestone for simulation in geometry nodes. But let's take a step back and look at what's actually been added in Blender 3.6 for simulation nodes. The new elements in the user interface that hint at the new simulation system are relatively subtle. In terms of nodes, there's really just a single new entry in the add menu to make simulation possible, the simulation zone. When you add it to the node tree, that creates two nodes that are already connected with a geometry link and this plum-colored panel that changes automatically when you move them around. This panel describes the so-called simulation zone, and it indicates which nodes are part of the simulation. When I insert the simulation nodes in here, nothing changes at first, because we are just passing through the geometry without doing anything. Let's just add an extrude node to make a visible change and use a random value node for a random selection of faces to extrude. You can see how the simulation zone adapts its shape to include the extrude node. The random value node, however, is not part of the simulation itself because it only provides a field that is used by the extrude node. The actual data that is part of the simulation is only passed around between these nodes here. But so far there is no simulation yet. But when I go to the next frame, you can see how this extrusion is done again and again and again the more frames I progress. The reason for that is that for each frame that I continue, the result of that previous frame is passed into its input, creating a sort of loop behavior. Each individual step of the operation is also called a simulation step. Okay, great, but I want to have a different random selection for each frame. So let's go to the random value node and plug in the frame of the scene into the seed input. And now when I continue frame by frame, you can see how a different selection is used for the extrusion on each step. But the result that we had earlier from the setup, using the same seed for every frame, is still influencing what we see here. The reason for that is that the simulation just takes whatever it gets from the previous frame, no matter what you changed. So to reset the state of the simulation to its initial state, we need to go to the first frame. And now if I play back the simulation, you can see how this works properly as expected. We get a different selection for the extrusion on every single frame. You can also see how in the timeline, playing back builds up this purple bar. And this bar is representing that the frames of the simulation are written to the cache. That means I can always go back in the timeline and get any state of the simulation without having to calculate it again. But this is only the case as long as the cache is valid. If I make any change in the node tree that affects the simulation, the color of this bar gets slightly more faded, indicating that the cache has become invalid and the simulation needs to be run again. But of course, if you want to, you can also just change the values in real time to affect the simulation that way. A more permanent way of storing the cache is to bake the simulation. That can be done in the Physics Properties tab under the New Simulation Nodes panel. This will bake the simulation data for the entirety of the scene frame range and store it on disk in a folder next to the blend file. We can also see and change that path here in the modifier panel. Now that the simulation is baked, you can see how the playback is super smooth, and when I change values, this will not actually invalidate the cache automatically anymore. So in this case, if you want to free it again, you need to do that explicitly by deleting the cache data. Let's go over another example to go a bit more into detail, where I show you how to build a relatively basic particle simulation setup using simulation nodes. Note, by the way, how what I've shown so far isn't exactly a physics simulation. The use cases for simulation nodes really go much further than what we classically have as a simulation in Blender. First off, let's just create a whole bunch of points, and for that I use the distribute points on faces node. With that, we can just create a bunch of points on the input geometry from the base mesh. And these points we then feed into the simulation. Inside of the simulation zone, the main feature of the simulation is going to just be moving the points. For that, we'll use the set position node. Let's just give that a go with just some random offset vector. And yeah, obviously right now this is not very interesting, but this is going to be the main concept. Just moving points in a certain direction. And to keep track of the direction and speed of that movement, we're going to add a velocity. The velocity is just going to be a vector attribute on the points. This attribute is also going to be part of the simulation. So the way to add this is to just click on either the simulation in or output, and then here in the sidebar, you can see that there is a simulation state panel that is new. And when I add another entry, this one pops up both on the input and the output. This is necessary because for the simulation step, everything that goes into the simulation output needs to pop up back out of the simulation input in the next frame. And then here for the socket type, I can just select a vector and call this one velocity. Now there's two things that I want to do with the velocity. First off, I want to keep it around for the next frame, so I'll pass it right from the input to the output. And then I want to use that velocity to move the points. To make this independent of the frame rate, let's use a scale node and scale that with the time that has passed since the previous frame. And then connect that into the offset of the set position node. Now I can just set the initial velocity for all the points in here. Let's say 1 unit per second in the x direction, and play it back like this. But so far nothing interesting is happening. So let's make some changes to that velocity instead of just passing it through. Let's just add a force like gravity. And the easiest way to do that is just use a vector input node, which will represent the gravity. And then we can use that to modify the velocity vector for each frame. Again, to make this independent of the frame rate, I'll use a scale node, scale that with the delta time, and then just simply add this to the velocity. That way we have a change in the velocity on each frame that is represented by this force. And if I replace this in the simulation output, you can see that this affects how the points are moving. So let's set this to something that kind of makes sense in terms of gravity. And that kind of looks right. Let's give this some velocity in the z direction as well. And there we go. So with a pretty small amount of nodes, we have a very, very basic setup already. So let's take this a few steps further. First off, I want to get a random initial velocity for each point. So for that, I'll just use a random value node. going into totally random directions. And then it looks like this. Another thing is I want to continuously add more points to the simulation. Right now we only get the initial state of the points through the simulation input. But this node is not the only way to pass in data into the simulation zone. Instead, you can also just pass it in directly like this. I'll just create a join geometry node and then join that together with the points that we get from the previous frame. And that way we add a new set of points every single frame. Again, this data is just what we get from the previous frame, or on the first frame from the initial step. And then the data that we pass in directly is calculated for each individual frame. So if I play this back, you can see how we get a new set of points joined together every single frame. But the set of points is always the exact same. So let's change up the seed for every frame. That way we get a random distribution every time. But you can see that only the first initial points get a random velocity in the beginning. The other points just start out with a velocity of 0. The reason for that is that we only pass in the random value to the initial points in the simulation input. Where the other points are joined into that same geometry, they don't have that attribute. So what we need to do is add a capture attribute node, set this to vector, and then in here capture this field as an attribute, and then add it together with the velocity of the other points. That way we combine the velocity attribute of the existing points with the new captured attribute of the new ones. And there we go. But let's make this simulation a bit more interesting. Right now we only have some initial conditions for the velocity and then a single constant force acting on the particles to change that velocity. Let's add some simple turbulence to them by adding a noise texture node. Let's connect the viewer to take a look at that. And right now the noise texture gives values from 0 to 1, but I want to center that around 0. So let's use a map range node, turn off the clamp, and put the from min 2.5. And that way we get nice values centered around 0. Let's connect the toMax to a value node, and then we can control the strength of this field. Now we can simply add this to the existing gravity force that we created before. And there we have some turbulence in our simulation. Change up the scale to make that a bit more clear. And to crank up the strength. Now that's a bit more interesting already. Another thing I want to do is keep track of each particle's lifetime. So on top of the existing data that we're keeping track of in the simulation already, I'm going to also add another attribute called the age, which is just going to be an integer to count up the frames. In the simulation, we're simply going to add 1 to the age for each frame. But now by default we have a bit of a problem that's not super obvious at first. But this little dot inside of the diamond shape indicates that we have a single value for each of the particles. It's not actually an attribute, it's just a single value. That is another feature of simulation nodes. You don't necessarily need to operate on your geometry data with attributes. You can also just simulate individual values. So right now, there's no way for the system to know that the age is supposed to be an attribute that is different for each point on this geometry. There's nothing that ties the age to the geometry right now. So to make sure that this happens, we need to use another capture attribute node. And then pass the age through that. And now you can see that the dot appeared. And now you can see that the dot disappeared because now this is actually an attribute on the geometry in the simulation. We can keep track of the age, for example, by connecting the viewer and then looking at the spreadsheet editor. So the points that exist from the very beginning just count up more and more. But if I scroll down a bit, you can see that the last points that are just newly created just have a single age of 1. Now this age parameter we could, for example, use inside of a shader to create all sorts of effects, like changing the color over the lifetime of a particle, or inside of the simulation. For example, to just delete some of the points when they reach the end of their lifetime. So let's create a delete geometry node and plug it in here to delete every point where the age is greater than, let's say, 20. So the particles stay alive for only 20 frames. And then they disappear. Now let's actually do something outside of the simulation itself. I want to make use of the velocity that we get for each particle. Now something that is important to note is that you should never use the velocity right out of the simulation zone itself to pass it out to some other node outside. Every connection that you make from inside a simulation zone to the outside will still be part of that simulation. So if you want to get data out of the simulation, the only way is through the simulation output, such as this. Note that this is different for the other way around. As I shown before, you can pass in data from outside of the simulation zone just like this, but out only through the output. Let's use the length of the velocity vector to get the speed. Use a map range node to map it to a smaller range that we can visualize like this. But let's use a color ramp for a better visualization. Let's just change the colors to something like this. And there we go. Let's crank up this density, by the way, to get a lot more points. Because this is a very simple simulation still, the performance is still quite good. Now, because we are piping through the actual group input geometry into the simulation zone directly like this, we also have direct real-time influence with the mesh. So if I just play the simulation and go into edit mode, you can see that I can change the mesh and see the updates in real time. So you can interact with the inputs like the mesh itself or all of the parameters that we're using in the setup in real time to affect how it behaves. Just as you would expect from a simulation. Let's add one more element to the simulation for some more interactivity. I want to add a separate force that is controlled with an empty object. For that, I'll just drag the empty into the node editor to get a object info node. I'll set this to relative to get the relative location, and then do just a little bit of vector math to get a force that draws the particles towards this empty. Let's take the location of the empty and then subtract the position of the particles. Now this vector, let's just normalize it and also get its length. And I want it to be stronger the closer the particles are to the empty. So I'll use a divide node and divide 1 by the distance and use that to scale the direction vector. Then just another scale so that we get more control over the strength. And let's add this to the existing forces. Let's mute this link, holding down Ctrl and Alt, right-click drag, to get rid of the original forces so we can see better what this does. Right now it doesn't do much because it isn't strong enough. So let's turn that up. And now you can see how the particles are drawn to the empty. Let's crank that up even higher. Now we got a really strong effect like this. Let's turn these initial forces back up for the full picture. And there we go. This is our final basic custom particle simulation setup. Of course, this is just one of the infinite use cases of what you can do with simulation nodes, but I hope this gave you a bit of a solid idea of what things you can do with it and how to work with them. In case you do feel like some of the things in this video went a little bit over your head, I can recommend you to check out the Geometry Nodes from Scratch course that we have on the Blender Studio platform. In this course I go over everything that you need to know to understand how geometry nodes work and how to work with them. But that's it from me. Have a great rest of your day and goodbye.